What's going on, everyone? Welcome back to the spot. We kick back and react to all kind of different things. All right, so what we got going on today? We're about to get into a science reaction with Neil deGrasse Tyson. All right, so this one is why uranium enrichment is a big deal. I don't know why, but we already know he's going to let us know why. He's going to break it down for us. So let's get into this. Neil deGrasse Tyson, why is it a big deal? Let's go.
You might have heard something on the uranium enrichment program in Iran and the centrifuges. So let me just put some of that in context in case you were wondering what's going on. So uranium, one of the elements on the famed periodic table, it has 92 protons in it. And the number of protons in an element defines the element. Uranium is traditionally considered the heaviest natural element. We look around the universe, do we see anything heavier than that? No, not really. We, however, are not content with what nature gives us. We want more. So in particle accelerators, we bombard the nuclei of elements and we can make heavier elements than uranium. And we've done so. Last I checked, we're up to 118. That's 26 more elements than the universe gave us. So, frankly, I think that's badass for humans.
It is badass. It's one of those things that makes the people paranoid too. Like, why are we messing with nature? If that's all the universe gave us, we should have stayed with that.
Primate brain, being able to come up with that kind of advance on something birthed in the universe. Anyhow, when you find uranium in nature, typically it's a uranium ore, it comes in completely mixed in three varieties. There's uranium 234, uranium 235, and uranium 238. Oh, by the way, these versions of uranium are called isotopes. Anytime you vary the number of neutrons in an atom, it's an isotope. They all have 92 protons, but all the rest of that number comes from neutrons.
Oh, okay. I was about to wonder why the number was so high, but okay, that explains it.
Way more than 92 neutrons. Oh my gosh. They're crammed into the nucleus. So many of these big elements are unstable for that reason. Okay, there's a lot going on in the nucleus, and the nucleus wants to spontaneously break apart into lighter elements. Neutrons, by the way, go wherever they want. If you were a proton, there's only so close you can get to the nucleus because the nucleus is positively charged and you're positively charged. You'll repel. So neutrons, since they are neutral, they are offered no resistance walking straight into the nucleus of atoms. So here is uranium 235 and it's hit by a neutron. What happens is the nucleus splits into two parts, two lighter atoms. If you measure the mass of those two lighter atoms, it is less than the mass of the original 235. Where did the mass go? Ask Albert. Hey, Einstein, where did the mass go? E equals mc squared. Energy is the mass times the speed of light squared, which is just a constant in that equation. So energy and mass are equivalent. And if you lose mass, you gain energy for having done so. Anything that's radioactive emits energy. So that's not what's interesting about uranium 235. If you split it, the splitting creates two or more new neutrons. If I have a collection of uranium 235 atoms, and I split one of them with a neutron, two neutrons pop out the other side, they hit two other atoms, now we're up to 4, then 8, then 16. This doubles fast. And you get what we named back at the birth of atomic energy, a chain reaction. And each one of those reactions releases energy. And given the kind of thinking that goes on in warfare, this wasn't simply a physics experiment that you write up in the journal. It was immediately weaponized.
Immediately weaponized. The folly of humanity, I swear, immediately weaponized. Oh man. Hey, we can disperse energy and it can do stuff. Well, can it destroy stuff? Perfect. Swear.
To create a bomb. So it turns out uranium-234 doesn't behave. You can split it, but it doesn't shoot out extra neutrons on the other side. So you'll get the energy from splitting one of them, but you're not going to create a chain reaction. Same problem with uranium-238. It's only the 235 that has this property. If you get enough uranium in one place at the same time and start the reaction, you light the fuse. If you want to
Basically like a natural bomb in a sense, because even though it's not the traditional explosion that we would expect, that release of energy, that radioactive energy, is what they're going for. To think we've come up with so many better ways to use it, but it always starts off with warfare. We always got to be violent first.
make a bomb, you want to isolate the uranium-235 from the uranium-234 and 238. Most of the uranium ore is uranium-238. Not useful for you. About no more than 1% of the uranium that is mined is uranium-235. So you want to enrich that. You want just the uranium-235. Well, how are you going to do it? These atoms are mixed together completely. How are you going to pull out the one that's in between the other two? Use a centrifuge. Well, centrifuges don't work on solid matter. You have to turn the matter into a fluid. It's a homogeneous substance that takes the shape of its container. So liquid is fluid, so is gas. The study in physics of fluid dynamics is the study of objects moving through gas and liquid. The same formulas apply in both cases. Back to uranium. One way to do this is to turn it into a liquid, but it turns out it's easier to turn it into a gas. Once you gasify the uranium, you now centrifuge.
Gasify, that sounds like a very serious stomach issue.
You spin it. The centrifugal forces will separate out the U-238 from the U-234, leaving the U-235 in between those two. So these centrifuges are complex bits of engineering to siphon out the uranium-235 in between the 234 and 238. Now, if you pull it out when it's enriched by 5%, that would mean what you've pulled out is 5% uranium-235. That's good enough for nuclear power plants. Sure. Want to make energy from fission? Go right ahead. Up the purity to 20% or more? That's enough to power sort of nuclear propulsion in, for example, nuclear submarines for the Navy. And the value of that is it can stay underwater for much longer periods of time before refueling. But to make a bomb, it has to be so purified that at least 90% of the uranium that's extracted is composed of uranium-235. So it all depends on your goal. We don't think of just living on Earth as a centrifuge, but in a way it is. On Earth, you live in a centrifuge of 1G. That's why your Italian salad dressing settles out, okay? The denser material goes to the bottom, the lighter goes to the top. That would be the vinegar, which is denser than the oil. You just centrifuged it by just setting it down in Earth's gravity at 1G. If it was 2G, that process would happen faster. Now, back to uranium. What's the mass difference between U-234 and U-235? It's one neutron. Yes, they have different mass, but it's a tiny fraction difference. So for a centrifuge to be able to separate them and distinguish the two, it's got to be really high G.
You know the old saying, a little bit goes a long way? That little bit of a difference makes so much of a difference when you really think about the ramifications of it all.
And in fact, the centrifuges invented to create weapons-grade U-235 can centrifuge so fast that the molecules themselves are experiencing nearly 1 million Gs. That's what you need to separate out these three isotopes so that you can isolate the U-235 in the middle. There are details I'm not sharing because they differ for different centrifuges, but the detail doesn't change the basic idea that I'm sharing with you. If you want...
In other words, as always, given the simplistic version so people can follow along. We're not going digging deep into stuff that's going to get too confusing. That's all. That's all.
To make a bomb, you have centrifuges. It's that simple. So, something as simple in concept as a centrifuge, which medical professionals use to separate platelets from your plasma in your blood, when taken to its extreme limits, who would have thought that a centrifuge can actually influence the balance of geopolitical power in the world? That's a bit of a cosmic perspective on this. What's up with that? Until next time, keep looking up.
And it's just a classic case of we discover something great and we use it for destructive means when in reality we could be doing so much better. It's just showing that, in my opinion, I always feel like things like that let us know that as a species we still have a lot of work to do. A lot of work. But as always, love getting a little bit of knowledge from these legitimate science channels. Always look for legitimate ones because there are some bogus ones out there. But yeah, Star Talk, Neil deGrasse Tyson, always great. But alright guys, you know what to do. Go down in the comment section, let me know what y'all thought about this one. And let me know what you'd like to see me react to next. Hit that like button before you go. Share this video with everyone you know. Subscribe if you haven't done so already. And if you really feel like supporting this platform, consider joining our Patreon. Alright, so till next time, take care of yourselves. And I'm out of here.